Good afternoon. Can you hear me?
Yes, sir, we can hear you.
Okay, thanks. Okay, so we'll begin. Um, so one quick announcement is that your assignment 2 is ready and it will be available for you at 6:30 p.m. today, and it's due by 9:30 p.m. So the last time we were discussing norms and matrix norms in particular. Today we'll continue our discussion on matrix norms. Just to recall, matrix norm is a mapping from the space of square matrices R to the n cross n to the real number line R. And we say that this a matrix norm, which is denoted by this symbol with three lines around it, this is a matrix norm if for any a and b in R to the n cross n, it satisfies these four properties. The first is that it is non-negative. The second is that it's positive, meaning that it can only be equal to 0 if the matrix itself is equal to 0. The third is that it's homogeneous. And the fourth is that it satisfies triangle inequality. So basically, any vector norm I start with will satisfy all four of these properties. So if I think of an n cross n matrix as a big vector containing n squared entries in it, and I define a vector norm on that, that will certainly satisfy these four properties. The only question mark is whether it satisfies this last property, which is called the submultiplicativity property, or not. So this is what we will examine today. So some vector norms are in fact matrix norms when you apply them on R to the n cross n, whereas others are not. So we'll start with the L1 norm. So remember that the L1 norm of a vector is the sum of the absolute value of all of its entries. If I simply extend that to an n cross n square matrix, then I would define the L1 norm of a matrix A to be the summation of all of its entries in magnitude. So the question is this a matrix norm or not? So the answer is yes. Of course, this norm as defined here does satisfy the non-negativity, positivity, homogeneity and triangle inequality by virtue of the fact that it is an L1 norm on in a vector space. So it directly satisfies those four properties, and so we only need to check whether it satisfies the submultiplicativity property or not. So I'll just write that here. 1, 2, 3 hold because is already a vector norm. So now about submultiplicativity. So what I need to show is that if I take any two matrices and I find AB L1, this is going to be less than or equal to the L1 norm of A times the L1 norm of B. That's what I need to show. Now this quantity AB L1 is the sum of the magnitude of the entries of AB, which is equal to sigma ij equal to 1 to n. So this is the sum over all the entries of this product matrix. But each entry in the product is the inner product between a row and a column of A and B respectively. So I'll write that like this. So if you remember, we discussed this different ways of writing out a matrix product. This is the way by which we write out every entry of the product matrix. Aik times Bkj. This is the I, kth entry of this product matrix AB. Now this quantity itself I can upper bound by taking the magnitude inside the summation. This is less than or equal to summation. Now because the summation will go over I, j and k, I'll just write them together. I, j, k equal to 1 to n mod of Aik Bkj. This in turn um, is less than or equal to, what I'll do is, see here it's index k and then there's a k repeating here. I'll just replace this k with an L and take the summation L going from 1 to n as well. What I'm doing there is I'm introducing a whole bunch of non-negative terms into this summation, and so that can only increase its value, it cannot decrease it. So I'll write this as sigma I j k L equal to 1 to n mod of AIL mod of BKJ. So this is a double summation over two indices. So I'll just make this a little neater. I j k L equal to 1 to n. Now this is just a, so notice that in the first term it depends on I and L. It has no j and k in it. The next term has j, k in it but no I or L. So this is actually equal to the product of these two terms, sigma I L equal to 1 to n mod of AIL times sigma jk equal to 1 to n mod of bkj. And this is nothing but, by our definition here, this is nothing but the L1 norm of A times the L1 norm of B. And thus AB L1 is less than or equal to the L1 norm of A times the L1 norm of B. So it satisfies submultiplicativity. And hence this A L1 as defined here is indeed a matrix norm. Okay. So we can go to the next possibility. So we did L1, now we can look at L2.
Sir,
Yeah.
the notation for the matrix norm will have three vertical bars, right? Why have you ignored the one of the bars?
Yeah, good question. So it turns out that I'm going to define the L1 matrix norm a little differently in a few minutes. Um, once we discuss something called induced norms. So it turns out that this is not quite the definition of the matrix L1 norm that I'm interested in. And so I have used a different notation. So for these norms that I'm discussing here, I will use only two bars to distinguish this norm from another notion of L1 norm on matrices that I'm going to define momentarily.
Okay, okay, sir.
So the L2 norm also I'm going to denote it with two bars because again this isn't quite the L2 norm on matrices that I'm going to later be interested in. But I'll define this to be.
Sir,
Is there another question? Yeah.
sir, sir, in the previous one, you have written like AIK, BIK, and you have introduced AIL, right? So what does it mean? I mean, for every AIK, you are replacing it with bunch of AILs, right? I mean, you are adding lot of AIs. Is that
Yeah,
what? Okay. So you are taking
exactly.
AIK and you are adding some other like AIs, right? AI1, something like that.
Yeah,
Is it?
yeah.
Oh,
There are
okay.
many. I'm
Okay.
adding n into n minus 1 terms into the
Okay.
summation, which will only increase its value. But they're all in magnitude, so none of them is negative. So it can
Okay.
only increase the value.
Okay, I got it. Thank you.
So the L2 norm I define like this. So it's so just like the vector L2 norm, which is the square root of the sum of the squares of all the entries. I define the L2 norm to be the sum of the squares of all the entries in the matrix, and then you take the square root. So is this a matrix norm? So once again, by virtue of the fact that it's this is an L2 norm of the vectorized version of the matrix, this will satisfy the non-negativity, positivity, homogeneity, and triangle inequality. Again, the only thing we need to look at is whether it satisfies the submultiplicativity property or not. And again, for this norm, it turns out the answer is yes. So we'll see that very quickly. So once again, if I take the L2 norm of a product AB, this is equal to sigma ij equal to 1 to n. So I'll consider the square so that I don't have to keep writing square roots. So this AB squared, if I show that this is less than or equal to L2 norm of A squared times L2 norm of B squared, that's also good enough for me. So this is ij equal to 1 to n. I have to take the mod square of this term here. So I'll just write the same term here. Sigma k equal to 1 to n aik bkj square. And now this is actually the square of the inner product between the ith row of A and the jth column of B. And I can use Cauchy-Schwarz inequality here and write this as less than or equal to sigma I equal to ij equal to 1 to n sigma say k equal to 1 to n mod aik square times sigma, just for convenience I'll replace k with m and write m equal to 1 to n mod of bmj square. So this is just from Cauchy-Schwarz inequality. Then notice that when I take this, if I take this, if I look at these two terms, this term has a summation over k, but it has no dependence on j. And this term has a summation over m, but it has no dependence on I. Okay, so I can write this as this is equal to sigma I k equal to 1 equal to 1 to n mod aik square times sigma j m equal to 1 to n mod bmj square. These two are exactly equal. It's just another way of writing this double summation with the summation inside of it. And so this is equal to a2 squared times b2 squared. So it does satisfy this submultiplicativity property. This particular matrix norm is actually called the Frobenius norm. Okay, so I'll maybe mention just one property of this norm. The property is that this particular norm is invariant to left or right multiplication by a unitary matrix. So one useful trick in this direction is that this norm AL2 squared is actually equal to the trace of A transpose A. Okay, so if you think about the entries of A transpose A, along the diagonals, you will get the sum of the squares of each column, the entries of each column of A. Okay, so because we are doing this online, I'll just maybe show you that very easily, very quickly. If I have A11, A12, A21, A22, okay, and if I take its transpose and left multiply it, that would be A11, A21, A12, A22. And then if I look at the diagonal entries, they will be, the first diagonal entry will be A11 squared plus A21 square. The second diagonal entry will be A12 squared plus A22 square. And so if I take the trace of this matrix, this is A transpose A. So if I take the trace of this is equal to A11 square plus A12 squared plus A21 squared plus A22 squared. And so it is exactly this Frobenius norm as we defined it here. So this is one useful formula. Now, what I wanted to say though is that if you have a matrix A and I write out its columns, A, A2 up to AN, then if I look at what this A2 squared is, this is actually equal to the sum of the squares of all the entries in this matrix. But I can also write that as A1 L2 norm squared, which is the sum of the squares of the entries in the first column of A plus A2 L2 norm square plus AN L2 norm square. This is another way of writing it. Now, the L2 norm by itself is unitarily invariant, meaning that if U is unitary, then Ux L2 norm is equal to the L2 norm of X itself. The way to see this immediately is that recall again that the L2 norm square in the vectors, for vectors, the L2 norm square is equal to X transpose X. So if I take the L2 norm of Ux, that is equal to X transpose U transpose Ux, and U transpose U is the identity matrix. So that's the same as X transpose X. So this is true for any unitary matrix and for the L2 norm. So we have that if I take the L2 norm of U times A square, then that is equal to, by using this formula here, it is equal to UA1 L2 norm square plus UA2 L2 norm square plus etc. plus UAN L2 norm square. So now I'm using the column view of matrix multiplication. When I multiply U with the matrix A, the columns of the product are equal to the multiplication of U with each of the individual columns of A. And so this is because this is equal to A1 square plus this is equal to L2 norm of A1 square. This is equal to the L2 norm of A2 square plus etc. plus the L2 norm of AN square, which is equal to the L2 norm of A square. So this Frobenius norm is invariant to left multiplication by a unitary matrix. You can similarly show that if I have if I take UAV L2 norm square, this is equal to a L2 norm square when, or I'll say if UV are unitary. Okay. So basically this Frobenius norm is invariant to left or right multiplication by a unitary matrix. Okay, so the next thing I want to consider is the L infinity norm. We looked at L1, L2 and L infinity. So we are basically covering most of these LP norms. For P not equal to 1, 2 or infinity, it's a little more difficult to figure out what's going on. So we don't, and usually in applications you don't encounter those norms. So we don't worry about too much about those norms. So this L infinity norm, if I simply extend the definition, it would be the max 1 less than or equal to ij less than or equal to n mod aij. The L infinity norm of a vector is the max magnitude entry, and so I'm extending that and saying the L infinity norm of a matrix is the max magnitude entry across the matrix. Now, is this a matrix norm? So for this particular example, it turns out that the answer is no. So once again, when you want to show that it's not a matrix norm, all you need to do is to provide one counter example where it does not work, and that is enough. So if I let the matrix, so if I consider J equal to the all ones 2 cross 2 matrix, then J square, what is J squared equal to? It's the all twos matrix, which is equal to 2 times J. So if I look at the L infinity norm of J as per this definition, it's the max magnitude entry, it is 1. But if I look at the L infinity norm of J square, it is 2, which is not less than or equal to the L infinity norm of J square. This was one of the requirements. See, if submultiplicativity were to hold, then the L infinity norm of J squared must be less than or equal to the L infinity norm of J times the L infinity norm of J, which is L infinity norm of J squared, but that is equal to 1 here, not bigger than 2. And so this is, as written here, this is not a matrix norm. However, a slight modification to this norm, if I define, now I'm using 3 bars to distinguish it from what I wrote above. If I write it to be n times A infinity, n is the dimension of A, A is an n cross n matrix, this is a matrix norm. So if I consider, so once again, because it's just a scaled version of a vector norm, the first 4 properties, namely non-negativity, positivity, homogeneity and triangle inequality, are naturally satisfied by this. So the only property we need to check is the submultiplicativity property. So if I consider AB infinity, then this is equal to n times the maximum entry in magnitude of the ijth entry of AB, and as we wrote above, this is equal to sigma k equal to 1 to n aik bkj. Now, first of all, I can, if I take the modulus inside the summation, I cannot decrease the value of the summation. So it is less than or equal to n max 1 less than or equal to ij less than or equal to n of sigma k equal to 1 to n mod aik bkj, and that in turn is less than or equal to, so what I can do is I can replace all these AIKs with the largest AIK value, the largest magnitude entry in the entire matrix. That will only increase the value of this summation. I can replace this BKJs with the largest magnitude entry of the matrix B. That will also further only increase the value of this summation. And so that is less than or equal to n max 1 less than or equal to I j less than or equal to n of sigma k equal to 1 to n a infinity, where this is the maximum magnitude entry, which is the norm a infinity with 2 bars as I defined it here, times b infinity. And now there are n such terms here, so I get an extra factor of n by removing this summation here. And so this is equal to n times a infinity times n times b infinity, which in turn is equal to the norm as I defined here times the norm as I defined here. Okay, so with a small modification to the definition, I can get a definition which is indeed a matrix norm. Any questions so far? So the next thing to talk about is induced norms. Basically, the idea is that we can associate matrix norms with vector norms through this notion of induced norms. So I'll define it here. So let be a vector norm on C to the n. So I'm taking complex. Like I said, a lot of the results here are applicable to complex as well. So I may go back and forth between these two, and where it's really required to make a distinction, I'll tell you the difference. Define on C to the n cross n as okay, so you take that norm, and if I compute that norm on the vector AX and take its maximum over all vectors which have a unit norm according to this vector norm, I'll define that to be this with 3 bars, this function with 3 bars on the matrix A. Okay, and so this is defined as the induced norm. So this is the so it's a I'll just put it in double quotes because I haven't really formally stated this yet. So this is the matrix norm induced by the vector norm okay. So this is the basic definition of an induced norm. Okay, so one thing you can immediately note is that if I scale x by some constant c, then the norm ax scales by the constant c, and the norm of x also scales by the same constant c. Another thing is that I'm trying to maximize this norm ax over all x such that norm x equals 1. I can as well maximize this over all x such that norm x is less than or equal to 1, because if there is some vector that solves, so let me write that here so that I can explain more clearly. Note is equal to max over all x such that x less than or equal to 1 of norm ax. That's because suppose you solve this problem and it gives you a solution for which norm of x is strictly less than 1. Then what I can do is I can scale that x by a factor which is greater than 1. Then the norm will may become equal to 1. But then when I scale that x by some factor greater than 1, then this norm of ax will also scale by a factor greater than 1. And since and that will only increase its value. So basically what that means is that the solution to this optimization problem will always occur at an x such that norm of x equals 1. So there is no loss or no harm if I include a whole bunch of other points which are inside the unit circle according to this norm, because those points will never be the solution to this problem. And this in turn can be written as the max over all x not equal to 0 of norm ax over norm x. Okay, this quantity itself doesn't change if you scale x. So I can as well maximize norm ax over norm x over all x not equal to 0. And finally, I can also, instead of maximizing over all x not equal to 0, I can also maximize over all x such that norm of x according to some notion of norm, I'll call it x alpha, equal to 1 of norm ax over norm x. So different ways of writing this. Is any vector norm. So there are different ways of writing it, but they all give you the same answer, which is what we are calling norm of A. So I've been calling it the norm of A, but actually we need to show that. So it's the theorem is that the function defined above is a matrix norm. Okay. On C to the n cross n and norm Ax. So this is a vector. So this norm here is the vector norm that induced this quantity here with 3 bars. This is less than or equal to the norm of A times the vector norm of x for every A and x in C to the n. So pick any vector. This norm of A is actually an upper bound on norm of ax divided by norm of x. If x equals 0, this is 0 and this is also 0. So it holds when x equals 0 as well. Also, the norm of the identity matrix equals 1. So remember previously we had said that the norm of an identity matrix is greater than or equal to 1 for any vector norm, any matrix norm. That's because the norm of I squared is less than or equal to norm of I times the norm of I, and therefore but I squared equals I, and therefore norm of I is greater than or equal to 1 for the identity matrix I. For these kind of norms, induced norms, norm of I equals 1. Okay. This is also known as, say, so this is called induced norm or operator norm. So I'll just write that here.
Sir, this definition of induced norm is valid for all type of vector norm.
Yes.
And sir, can you please explain that node part again? I could not understand that why this max of norm of x less than equal to 1 should be equal to norm of a.
So the by definition, this is the max over all norm x, all vectors x such that norm x equals 1. Okay, and I have to find this norm ax. I search over all vectors which have unit norm and find the vector that maximizes the norm of ax. Now, instead of searching over all vectors x such that norm of x equals 1, suppose I search over all vectors for which norm of x is less than or equal to 1. Okay, that includes, so I guess, first of all, a very intuitive and simple way of thinking about it is, suppose I consider this norm to be the L2 norm. Then basically when I say norm x equals 1, I'm asking you to search over points lying on this circle. Okay, and A is some matrix. And among all the points on the circle, I'm asking you which point maximizes norm AX. Then basically as you go further and further out on the circle, this norm of AX will also increase. So if I take a point X here versus a point X here, the norm of AX over here will be bigger than the norm of AX over here if these are on the same line, the same direction. So if, for example, when you solve this problem, if you get an, if you say my solution is some particular x hash such that norm of x hash is equal to some value, say b, which is less than 1. Okay, so then this the maximum is happening at an interior point. Then then what I can do is I can propose a better solution. I can say my solution is x dagger, which is equal to your 1 over b times x hash. If I do this, then if I look at what happens to basically norm of ax, this is equal to 1 over b times norm of ax hash. So whatever maximum you found, I am able to find an x dagger. Notice that this also satisfies my constraint, is actually equal to 1 over b times the norm of x hash, which is equal to b, and so this is equal to 1. Okay, so this satisfies the constraint that norm of x should be less than or equal to 1, but the value of the objective function ax dagger is going to be strictly greater than ax dagger itself. So whatever solution you found, I am able to find a solution that beats your solution. It achieves a higher maximum. And as a consequence of that, the solution to this problem will always occur at a point where norm of x equals 1. And so you don't lose anything by saying I'll maximize over all x such that norm x is less than or equal to 1. It will always give you the same solution as the earlier optimization problem.
Yes, sir.
Also,
Thank you, sir.
yeah, I don't have to restrict to x less than or equal to 1. I can maximize over all x not equal to 0 by simply including norm x in the denominator of this objective function. That is the idea. Okay, so this is the theorem. So basically whatever we defined earlier is in fact a matrix norm. Okay, so let's check this. So again, we need to verify non-negativity, positivity, homogeneity, triangle inequality, and submultiplicativity. Okay, now obviously,
Sir?
yeah.
Sir, some places matrix norm is with double bars and some places with triple bars. So could you explain that?
It's always with triple bars, except when I was giving a couple of examples here. Okay, and somebody else already asked the question. I suppose you weren't paying attention. And I explained that I'm going to use a different, I'm going to define the L2 norm of A with 3 bars in a different way. And so I'm saving the triple bar here for that purpose. And so here this AL1 and AL2 I have defined with 2 bars because I'm going to use a different, I'm going to define a different norm for the L1 norm and L2 norm. Okay, otherwise matrix norms are with triple bars.
Okay, sir.
Okay, so now these are the 4 properties. So first we'll take non-negativity. So obviously by definition, the norm of A is the maximum of a non-negative quantity. This norm of Ax, this is a vector norm and it's a non-negative quantity. So when I take the maximum of a non-negative quantity, I cannot suddenly get a negative quantity. So it is non-negative. And the positivity is because the this norm of A will be equal to 0 if and only if Ax equals 0 for all x, x not equal to 0. So for that, the simplest way is to consider this version of writing out norm A is the maximum over all x not equal to 0 of norm Ax over norm x. So for this maximum value to be equal to 0, the value itself must be equal to 0 for all x. Now, if norm A has to be if norm of Ax is 0 for all x, it means that Ax itself, this is a vector norm. It means Ax equals 0 for all x. So, and this is true if and only if A is equal to 0. Why is that true? Why should Ax equal 0 for all x mean that A is equal to 0?
Positivity property of the vector norm, sir.
No, there is no norm here. I'm just saying that a matrix A is such that if I find Ax, it gives me the 0 vector for all x. And I'm saying, I'm
We can
concluding
express
that
the columns of the matrix as the transformation of the basis elements.
I don't follow that.
Any matrix, if we act the matrix on the basis elements, then we'll get the columns of the matrix. And if all of them are 0, then the matrix will be 0.
So you're saying that you want to think of a basis in say C to the n, and you want to project the columns of the matrix on this basis. And
Yes,
from that somehow conclude that Ax equals 0 means A equals 0.
yes, sir.
Well, I can think of a simpler way of saying that. So
So
suppose
range space of a 0 means is 0 always.
yeah, so I'm asking why is that true? And so one very simple way to see that is that if I take x equals the vector 1 0 0 0 0 0, then what that will do is to pull out the first column of A. Since Ax equals 0 for all x, it's also true for this vector 1 0 0 0 0. That means that the first column of A must be 0. Next, if I consider x equals 0, 1, 0, 0, 0, that ax for such a vector will be equal to the column a2, but that's also equal to 0. So the second column is also equal to 0, and so on. So if ax equals 0 for all x, then a is equal to 0. Similarly, I mean, the contrary is trivial, because if a is equal to 0, then of course ax is equal to 0 for all x.
Yes, sir.
So
I meant the
that,
same proof.
yeah. So the next property is homogeneity. So we need to show that if I consider the norm of C times this matrix A, this is equal to the max of, so I won't write the constraint here because it's just repetitive. It's the same constraint, x norm of x equals 1. So I won't write that. CAX, and this is a vector norm, so I can pull out the C and write this as mod C, and this mod C doesn't depend on x, so I can in fact pull it out of the max also, times the max of AX, and this is actually equal to mod C times norm of x A. So it does satisfy the homogeneity property. This by definition is the norm of A. Then triangle inequality. If I take A plus B, this is equal to the max of norm A plus B times x, which is equal to, okay, so this is the norm of AX plus BX. And if I use the triangle inequality, this is less than or equal to the max of norm AX plus norm BX. In turn, this is less than or equal to, so instead of maximizing the sum of these two quantities, I can individually maximize these two terms and add them up. That can only increase the value. So that is max of norm AX plus max of norm BX, and this by definition is norm of A plus norm of B. So it satisfies the triangle inequality and submultiplicativity. So if I consider norm of AB, this is equal to max of, I will consider the other form, so I'll write it like this: ABX over norm x over all x not equal to 0. So this is equal to, so for a moment let's say bx is not equal to 0. Then I can multiply and divide by bx by norm of bx, and now I have the max of the product of two terms, and what I can do is I can individually maximize these two terms. They are non-negative terms. So instead of maximizing the product of these two terms, I can individually maximize these two terms and then take the product of the two maxima. That will only be greater than or equal to this term. So I can write it like this. And of course, I can consider bx to be some other vector y and maximize over all y not equal to 0. So max of norm ay over norm y times max of bx over norm x. and this is equal to A. Okay, but of course if Bx is equal to 0, then ABX is also equal to 0. And so this quantity you're trying to maximize, this will be 0. And so such kinds of x's can be discarded safely from this maximization problem. They won't be the maximum. In fact, they are achieving the minimum value that this can achieve, which is 0. Okay, and the final part is that there is this the statement of the theorem also says one inequality, which is that the norm of Ax is less than or equal to the matrix norm of A times the vector norm of X for every A and X. We need to show that. Of course, that is trivial because if you consider norm of Ax over norm X, this is norm of Ax divided by norm X, and this is less than or equal to the matrix norm of A, because by definition the right hand side is the maximum value of the left hand side over all x not equal to 0. And so for any A and X, this is true. And so I'll write that just for completeness. The RHS is the max of the left hand side by definition. So the maximum of a certain function is always greater than or equal to the value attained by it at any particular point. So this of course assumes that x is not equal to 0, but clearly this inequality is valid when x equals 0 also. Clearly this Ax less than or equal to norm A norm X holds when x equals 0 also. So basically this in turn, I can simply take this norm of x to the other side, and hence norm Ax is less than or equal to the matrix norm of A times the vector norm of x. Okay. And finally, if I consider the norm of the identity matrix, this is equal to the max over all x such that norm of x equals 1 of the norm of identity times x. But this is just norm of x itself. So the constraint set says norm of x, I mean you are maximizing over all x such that norm x equals 1 of norm x itself. And so this is equal to 1. So that concludes this proof. Any questions? Okay, so this matrix norm is said to be induced by the vector norm. So it's also called the operator norm, or it's also called the least upper bound norm. Okay, this is basically the least upper bound norm. This name comes from the fact that by definition this norm is the maximum over all x equal to 1 of the norm of Ax. So in other words, it's the smallest upper bound you can place on norm of Ax over all x satisfying norm x equals 1. Or if you look at this definition here, it's the smallest upper bound you can place on norm Ax over norm x over all x not equal to 0. So that's why it's called also called the least upper bound norm. Okay, so basically the fact that the operator norm or the induced norm is a matrix norm is a general property, and it's true for all vector norms. And so one way to show that some particular definition of a norm is indeed a matrix norm is to show that it is in fact induced by some vector norm. And so now we have another way to show that. So one way to show something is a matrix norm is to show that it is induced by some vector norm. So here's an example. So now I'm going to introduce the L1 norm with 3 bars. So this is called the max column sum norm. So I'm going to denote this by with 3 bars and the one next to it. So it's defined as max 1 less than or equal to j less than or equal to n of sigma I equal to 1 to n mod aij. So this what I'm doing here is I am taking the sum of the magnitude of entries in each column of the matrix. So when j equals 1, it's the first column. I'm taking this L1 norm of the first column, and I'm looking across all columns, first, second, third, up to the nth column. I'm asking which column has the maximum L1 norm, and I'm defining that to be the matrix L1 norm of this matrix A. So this is induced by the vector norm L1. So to quickly see that, if I have A equal to A1 AN, then this norm A1 is equal to the max 1 less than or equal to I less than or equal to n of the L1 norm of AI. As I just mentioned, this norm here is taking the max column max of the L1 norms of the columns of A. The largest L1 norm among the columns of A is this matrix norm. Now if we let x to be equal to this vector x1 through xn, then if I look at Ax L1, this is equal to the L1 norm of x1 A1 plus xn an. The entries of this vector x multiply the corresponding columns of A. And this in turn is less than or equal to, I'm using triangle inequality, sigma I equal to 1 to n L1 norm of xi ai. So I've just taken the norm inside the summation, that's triangle inequality, which is equal to, now xi is a scalar here, so I can pull that out, sigma I equal to 1 to n mod xi times the L1 norm of ai. which in turn is less than or equal to. So I can replace all these by the largest column norm, and that will only increase the value. So sigma I equal to 1 to n mod xi times the max 1 less than or equal to k less than or equal to n norm of ak. And this by definition is the L1 norm as defined here. It's the max column sum. And so this is equal to the L1 norm of x, the sum of all the entries. It doesn't depend on I anymore. This can come out of the summation times the matrix norm of A. So what this means is that for any x, the L1 norm of AX is less than or equal to, so I'll write that this implies, this is true for any x. The L1 norm of AX is less than or equal to the norm of x, the L1 norm of x times the matrix norm of A. And so it is also true that if I take, since it's true for every x, if I take the max over all x such that x L1 equals 1 of the norm of AX, this is going to be less than or equal to the matrix norm of A. But I want to show that these are actually equal, that this definition that I have here is in fact induced by this. For that I need to do a little bit more work. So now let x is equal to ek, k equal to 1, 2 up to n. So this ek is the kth column of I. So then what I have is that max norm x equals 1 of ax is at least equal to the value it takes at one of these, an example vector, which is for example e1. If I take e1, that satisfies L1 norm of e1 equals 1, and that will give me the L1 norm of the first column of A. So if in general if I take the kth column, then it will be AK L1. Okay, so this is also true. And so then this is true for all of these k equal to 1, 2 up to n, which implies that this maximum of this is greater than or equal to the max 1 less than or equal to k less than or equal to n of norm ak L1, which by definition is the matrix norm of A. So I have shown that this max of this is less than or equal to norm of AL1. I've also shown that this max of this is greater than or equal to norm of AL1. So if I call this step A and this step D, these two together imply max 1 AX L1 equal to. So this shows that the max column sum norm as I defined it is in fact induced by the L1 norm. Okay, so it's an exercise for you to show that this is a matrix norm by showing that it satisfies the 4 properties for a matrix norm. Okay, so that's all I have time for today. I'm actually a little over time. So I think Friday is another institute holiday, so we won't be meeting on Friday, but we'll meet again on Monday of next week. Okay, that's all for today. Thank you and have a good rest of the day.
Thank you. Thank you.